Hello again. I just want to update. Yesterday I fixed the Lexer, and as you can see I have a lot of different tokens that I currently accept. I have numbered them all so they have a descriptor identifying them. And yeah, these are all the tokens so far. There's actually more, but these are just the first step of actual parsing. I have added some others in the actual parser. But so far these are the different tokens I can recognize. So I can just test it out, show you guys. Let's see, hopefully this will work. Ooh, let's check. Alright, so we have the first token, the second, the next, next, if, curly bracket, yes, print, while, plus, minus, divide, times, and less than, greater, and let, or my name, and enough bars. So yeah, I'm very happy. I had some problems. It's primarily just because it's not really a problem, but it's difficult to code in assembly because you have to keep everything in your head all the time. So whenever let's say I tokenize this token, a plus, sometimes it would actually recognize as this token instead, the equals token. And that had something to do because the way I have written it here is actually it checks for this string and it matches this string against another string. So it can get kind of confusing sometimes how long a token is. Like, is this actually one character or two characters? Because there's the null terminating character. I also have had some difficulties in actually deciding when to progress to the next. Like, when I pass this token, should I stop here or should I go to this step? However, if I progress to the next one, like go here, then I wouldn't be able to pass something like this, because then it would read plus and a 3 at the same time. And just show you that it actually also works. It should work. Nope. And it doesn't work because main. It's because I have nothing. I didn't want to write it to print number. It's involved to do that, but I can show you by doing this. A and B. Yeah, A plus B. Nice. So, anyways, the tokenizer works, so I'm very happy. Yeah. It's very long. 500 lines. But then again, remember, it's just a copy paste most of it. It's divided into 2 sections, 3 sections maybe 4 even. The first step is to remove any white space. So for example, if we check this string out, like whenever we read this token and we want to go to the next token, we just ignore all of this white space. That is basically what this does. The number 32 here is referring to this number here, space. So actually I'm not able to ignore tab characters. I should probably do something about that. this tag. Yeah, I don't know. I will figure that out later. It doesn't really matter. So that's the first part, and then let's see here. We call a method called identify token, which is defined down here. It's just going to go through each of the different tokens I have defined over here. So the first one, am I currently seeing this token or this sequence of characters? If not, then I will progress to the next one. Am I seeing this sequence of characters? If I am, then this will return a 1, otherwise it will return a 0, so I compare it to a 1. If it's a 1, I jump to something called return if token, which is down here I can see, which basically the compare string method actually increases the buffers I put into them, so I can actually use that to store the address of where I have reached. And then I just put the identifier for the token into the rax, which is the return register, and we can see here that's the 2, and then it just returns. And then when we come up here, after we have checked for all our tokens, we check for -1, and that is basically end of pass token. So if we have reached the end of pass, we are just going to return. However, if we received a 0, then it means that we didn't read one of these predefined tokens, and that means that we didn't find a token that we matched on. So it can either be an identifier or a number, which is this we come to now. So first we check for the first byte. That could be something like this, a 6. And then we're just going to check, are we inside the number range? Okay, it seems that we are. Alright, then we just go to the loop to determine how long the number is. Yeah, so basically this just, you can see here, it loops from here to here until it sees that it is not a number anymore. Basically it's outside the bounds, the char bounds, which are these. If it's outside this, then we know it's not a number and we can skip it altogether. Or we can say submit. Now we have read our entire number, so for in this example it would be a 6. And then we go to the next phase, which is called submit the number. So we convert the character representation of a number into 2's complement representation of a number. Yeah, it's not really that difficult. We just subtract it, because as we can see, it's offset. So 0 is 48. So if you read a 0, we subtract 48 from it, we get a 0. In this case, reads a 6. A 56. 56 minus 48 is 6. Yeah, so we get a 6 here. And then we can this is the process of imagine we had this number, then it's actually 600 plus 10 plus 2, and that's the reason why we have to multiply this by 100, and this 1 with a 10 and this 2 with a 1. So that's what we're doing here. And then once we're done, we are going to call the method down here, which is called insert number. Which is this function. So first, let me just tell you, I have because assembly is kind of difficult, you can really, well, it's difficult to do anything at runtime. So what I do is I just statically allocate a huge array. For this example, it's number of tokens. So it's basically just a token array full of integers, descriptors I call them. I do the same for identifiers. So you could imagine, for example, identifier is just an array where you see a bunch of zeros. And then if you want to write something in it, so let's say I have a variable, then it's going to do insert this into it. And then it's going to return the descriptor 0 because this is the index into it. If I have some other variable here, then it's going to return the offset of this character. So that way we can have any length as long as it fits inside this of variable or identifier names. So that's very cool. Yeah, so that's basically what we're doing. Where is it? It's here. So first we find the it's this one. We find the buffer for our number tokens, and we store it in racks, and then we find out how many numbers have currently been placed in the buffer, and we can find it here because it's currently 0. So now we have 0 in this register, and then we just move the input, which is the number, into the buffer. And we can see here there's an offset of 4, meaning that we take the offset to the address, which is the start of the buffer, and then we are going to multiply the current number count inside, or the size of the array, by 4, because a number is basically 32 bits. Yeah, 4 bytes because of that. And then we just update the number count, and we return a number descriptor representing this number. And that's the same as we do with identifiers. However, now we need to we also need to move the chars over there, which is basically this. Move the byte from the source, move it to the target, increase the counter. Yeah, here we actually get the count, how many characters there are. So that's nice. Basically this function is meant to be called once, or one for every time you want a token. So you would have to call this function for the number of tokens there are. So in this example there are 1, 2, 3, 4 tokens. So we would have to call this function 4 times to get all the tokens. And the reason for that is because it makes it easier to actually develop the parser, which I already have begun, but I guess I won't show it in this little update because it will make the video too long, and I guess it's very digestible in these short formats. What I can say is that it's a good idea to draw some notes as you go along, and maybe really spell it out for yourself, because that really helps a lot. Like you can see all the notes I have for myself. Yeah, this is just giant clusterfuck, so it's not really important. It's easy to figure out what's going on. Oh yeah, I can show so if we return a number token, we will move we can see here in the rags register is the token ID, so it's these, and in this case it's going to be number 25, and the descriptor, which we get from the actual call up in the Lexer, which is the, as I said earlier, the offset into the buffer, so we can always refer to it. Yeah. I can also show you this very nice diagram I made. Yeah, so this is a little sneak peek of my parser. Currently, I can actually parse the token or the expression. I think I have written it. Where is it? No, I removed it. Okay, I made this grammar file. It basically describes the grammar for my language that I'm going to develop. And I'm going to start with just doing a statement, and which is going to be the start of my program. So a statement, it's going to be a statement which goes into this. So a statement, it is an identifier, so a or something else, a variable name, is equal to, and then some sort of expression followed by a semicolon. And this expression is going to, for this case, I'm going to develop the number and then also the expression binary operation expression. So I can basically add two numbers, or I can parse it and then I can store it into an identifier. So it's an assignment. This. Yeah. So it's actually not that difficult. You just have to really think about it. You can see here I made a new descriptor or a new type of token, which is number 26. It's a binary operation. The type of a binary operation is a descriptor, and then the layout for a binary operation is this is not a part of it, but these fields here. So first, and that's actually wrong, but it is okay. Down here we can see the layout, but this is how the internal, like how I thought about it, what it needs. It needs an operator, which is a token ID. It can be this token, this token, this. It can also be this or this or this. And yeah, here we can see how I store it in memory. So it's just a bunch of integers. So first the left hand side, ID, the token ID, and then its descriptor to understand what is it. The first one tells, is it a variable or is it a number? And then I can look up in the corresponding buffer with the descriptor for it. And that way I can find out what is stored in that number or in that token. So it's kind of, I'm going to have a lot of different buffers for this program or this compiler. After that we have the operator, and then the right hand side ID and the right hand side descriptor. It's kind of arbitrary the order of this, but it really doesn't matter, just as long as you remember it. That's why I have written it down. And then I have an expression which is type 27, token ID type 27, and then it's going to contain the type of the expression. It could be a binary operation. It could be, like if we look here, there's this, which is a function call. There's also this, which is a function call with parameters or arguments. And then there's this, which has precedence over other expressions. So evaluate me first, basically. Yeah. That's it, I guess. That's how far I gotten. Currently the actual parser actually works. I get into it. I call the parse function, which is this one, and I just call parse expression because I just want to be able to parse something. Yeah, and how it works, it starts by calling this function, which is it's just a wrapper function for calling the get token from the Lexer, and then it's going to move the token ID into the current token I have stored, and then it's going to compare if it actually needs to store some data, because all of these tokens don't need to store any data, but the identifier and the number needs to store data. If that's the case, so number 25 or 24, these two, then we jump to set descriptor, which is basically move the EBX register into the destination, into this. So it's basically global variables. So this is an integer, this is an integer, and it just stores the current token ID and the current token descriptor. Yeah, so it starts by first getting the token. Okay, we have the token. This is actually wrong. I think this is left over from yesterday. I don't actually remember. Anyways, the goal of this is to parse the expression this, so number operator, and then it's actually expression operator. Thus we also need the number here. So we are able to first pass the number as one of them. So this will get replaced by a number, and then we see, okay, it's an operator, and then we have also passed the next number, and then we have successfully passed it. So we start by pushing the data, the current token that we already read, and then we are going to try to, so this is the current stack, then we are going to try to pass the next token or get the next token, and then we're going to look at it. If the next token is a plus, minus, star, times one of these operators, so these are the operators. If it's not an operator, then we know we shouldn't be doing any of this, and for that reason we can just return the token descriptor and the ID and just leave. And that could maybe be the case if we did this 1, 2, 3. Then we would just do an expression into the number 1, 2, 3. However, if it read a plus, then it assumes that there's going to be an expression after this. So we hit this one, and then we go down here, and then we're going to push the number 13. If we look down here, that's the ID for this token, and then we are going to jump up to done with operator, which is here. And then I had made a note for myself, so we can see here, this is the current stack layout. So I have on the very top level, I have the operator ID, and then I have the token descriptor and the token ID for the left hand side. I haven't figured out how to handle precedence yet, but I will get to that. And at this point, it's just another call to parse expression, because it could be a sequence of 2 plus 2 plus 3 plus 4, maybe, right? So it's going to first pass this number, and it's going to check, is it an operator? Okay, it is. Then we store these two tokens on the stack, and then we're going to call parse expression. At this point, this is going to check if this is an operator. If it is, good, go ahead. Oh, we didn't see an operator. In fact, we met an end of parse, and then we're going to stop here with this for. And I can see that I want my structure to look something like, let's just do this. I want the 1 and 2 to be combined, and with a plus, and then I want this to be combined with a plus to the 3, and I want this to be combined with a plus to the 4. So that way we can see this is the pass. We see, okay, we want to add something, and we want to add something, okay. We want to add 1 with 2, okay, it's fine, it's 3, and then we want to add the 3 here from these two. We want to add those together, so we get a 6 here, and we want to add 6 and 4, so we get a 10 here. That's basically the idea of parsing. So that's the tree I want. Yeah, I could also go for it on the other side. Let's see. That might actually be a better idea. I don't know yet. I will figure that out. Yeah, after the call to parse expression, we will get the next. So we push the token ID and the descriptor. So now we have this on the stack. So the right hand side, the operator, and the left hand side. And then we can just pop them into some registers and then call the construct binary operator method, which is going to return a descriptor. And then we can push a token descriptor, and we can push the number 26 because that is the token ID for a binary operation. And then we can push the token ID, and then we just leave. And then we have successfully parsed a binary expression. These functions are very simple. It's just the same as the insert number from before in the Lexer. We just move the stuff in the correct spot. And the same with the push token ID, we just move the value into the variable. And the same as descriptor. I also have something to return the current token and the current token data. Just shorthand, so I don't have to write the same logic all the time. It also makes it easier and ensures that I don't make any stupid mistakes. Yeah, so anyway, that's how far I've gotten yesterday. It didn't actually take that long, so that's really nice. Yeah, anyways, see you next time.